Alright, non-resident training course, September 1998, Navy Electricity and Electronics Training Series, Module 2, Introduction, Alternating Current and Transformers, um, Navy, NAVEDTRA 14174. We're on Chapter 2. Chapter 2, Inductance. Learning objectives. Upon completion of the chapter, you'll be able to write the basic units assembled of inductance, state the type of the moving field that uses the generator of the EMF and a conductor to determine the term of inductance, state the meanings of the term induced EMF and counter EMF, state Lenz Law, state the effect of the inductance has on steady direct current and direct current has in changing magnitude. List the 5 factors that affect the inductance of a coil. See how various physicals will change if these factors affect inductancy. State the principle of sequence involved with the buildup and the decay of the currents in the LR series circuits. Write the formula with the computing one time in the LR series circuits. Solve the L over R time constant problem. State the 3 types of powers lost in an inductor. Define the term mutual inductance. State the meaning of the terms coupled circuits. State the meaning of the terms coefficients of coupling. Give the inductance values and coefficients of the coupling between 2 series connected with the inductor. Solve the mutual inductance for M. Write the formula of the total inductance. 2 inductors connected in series opposing. Give the inductance values of the mutual inductance value between the 2 coils connected in series A to solve the combined letters of the load total, or L total. I think that's what it stands for. Alright, the study of the inductance, inductance. The study of the inductance present with the vary the channel with the rewarding segment of electricity, the change with the sense of that at first it will seem the new concepts are being introduced. You will realize that as the chapter progresses, the new concepts are merely extensions and enlargements of the fundamental principle that you've learned previously in the study of the magnetism and electron physics. The study of the inductance is rewarded with the sense of through the understanding of it will enable you to acquire the working knowledge of electrical circuits more rapidly. Characteristics of inductance. Inductance is the characteristic electrical circuits that opposing starting and stopping changing the value of the current. The above statement is the such important for the study of the inductance that bear for the repeating inductance is the characteristic for the electrical conductor with opposed to the change in current. The symbol inductance is L. The basic units of the inductance is a Henry or H. 1 Henry is equal to the inductance required to induce 1 volt into an inductor required to induce 1 volt into an inductor by changing the current of 1 ampere per second. Alright, so it's 1 Henry is equal to 1 volt inducted in the change of the current in 1 amp per second. You do not have to look far to find physical analogy with inductance. Anyone who has ever had to push a heavy load, wheelbarrow, a car, etc., is aware that it takes more work to stay with the load moving than it does to keep it moving. Once the load is moving, it's easier to keep the load moving, and then it stops again, and then to stop it again. This is because the load processes property with the property of an inertia. Inertia is a characteristic of the mass with opposed to change in the velocity. Inductance have the same effect of the current with electrical circuits as an inertia has movement of the mechanical object with require more energy to start and stop the current than it does to keep it flowing. What is the basic unit of inductance and the abbreviation for this unit? That would be L, and Henry is also in 1 volt inductance to change a current of 1 amperes per second. Electro-motive force. You have learned the electro-motive force is developed whenever the relative motion between the magnetic field and a conductor. Electro-motive force is the difference of potential voltage which exists between 2 points in an electrical circuit. The generator, inductor, and EMF is developed by the action between the magnetic field with electrons and a conductor shown in Figure 2.1. 2.1 shows the generation of EMF in an electrical conductor. Show the battery, the original amperes in a circular motion, inducting induced electron flow would go is headed down the magnet. Okay. When the magnet field moves, the stationary metallic conductor electrons are dislodged from their orbits of electrons moving in direction to determine the movement of magnetic flux, and this is shown by direction of movement, flux, magnetic flux, conductor. The electrons move from one area of the conductor into another. The area of the electrons move with the fewer negative charges. Electrons becomes positively charged. The area electrons move into becomes the negatively charged. This is shown by positive and negative. The difference between the charges in the conductor is equal to the difference of the potential of the voltage. The voltage becomes a moving magnetic field is called electromagnetic force. In simple terms, the action of moving the magnetic field on the conductor can be compared to the action or the broom. Considering the moving magnetic field to moving the broom is a magnetic broom that moves along through the conductor and gathers up, pushes electrons before it is shown below. Alright, the area from the electrons move becomes positively charged, while the area in which the electrons are moved becomes negatively charged. The potential difference between the two areas is the electro-motive force, or EMF. When EMF is generated with the conductor when the conductor is cut, but what type of the field? Self-inductancy. Every perfectly straight with a conductor, but it has some inductancy. As you know, that the current of the conductor produces. As you know, the current in the conductor produces the magnetic field surrounding the conductor. When the current change with the magnetic field change with the causes of the relative motion between the magnetic field and the conductor and the electromagnetic force, EMF is induced for the conductor. The EMF is called a self-induced EMF of the basic for the induced for the conductor carrying the current. The EMF produced the sum of, by the moving the magnetic field with the reversed is the EMF produced by the moving the magnetic field is referred to as counter electromagnetic force. The polarity of the counter electromagnetic force is in the opposite direction of the applied voltage of the conductor. The overall effect of the will oppose the change of the current magnitude of the effect of the summary of the Lenz Law, which states the induced EMF any of the circuit always is in the direction to the opposing of the effect that it has that produces it. If the shape of the conductor changes to form a loop of the electromagnetic field around each of the portion cuts across some of the other portions over the same conductor, shown in the simplest form, figure 2.2. The length of the conductor is looped in two portions, and the conductor lie next to each of these portions are labeled the conductor 1 and 2. Conductor 1 and conductor 2. The switch is closed in the current electric flow in the conductor produces the magnetic field around all portions of the conductor. For the simplicity, the magnetic field expanding the line of flux is shown with a single plane with a perpendicular in both conductors. Although the expanding field of the flux originates in the same time with both conductors, it is considered the origination of the conductor 1 and its an effect for the conductor 2 will be explained while increasing the current of the flux field that expands outward from conductor 1 cutting across the portion of conductor 2. This results in induced EMF of the conductor 2 shown by the dash arrow. Note that the induced EMF is in an opposite direction in the opposite to the battery current voltage stated in Lenz Law. Alright, show the direction of the magnetic field of the induced voltage, the left-handed Fleming law, direction relative to the conductor motion, direction of the flux expansion, conductor 1, current, conductor 2, induced EMF, switch closed, current increase, and the battery on the line. Direction of the magnet, the direction of flux collapses, direction relative to the conductor motion. Direction of induced voltage may be determined by the left-hand rule for the generator. The rule has the portion of the conductor that is lifted and enlarged, and for the position and purpose of figure 2.2a, the rule states that if you point the thumb of your left hand in the direction of the relative motion of the conductor, you induce the finger in the direction of the magnetic field. You will mind the finger with extends as shown. You also indicate the direction where the induced current will generate the induced voltage EMF is shown. In figure 2.2b, the same section of the conductor is shown as after the switch has been opened. The flux of the field collapsing after applying left-hand rule. In this case, show the reversal of the flux of the movement that has caused reversal of the direction of the induced voltage. The induced voltage is known as in the same direction of the battery voltage. The most important thing you can note too is the self-inducing voltage opposed to both changes in the current. This is when the switch is closed, the voltage delay for the initial build-up of the current opposing the battery voltage. When the switch is open, a current flowing for the same direction by aiding the battery voltage. Thus, the above explanation, you can see that the current is building up and proof that it is expanding magnetic field. The field induced for the EMF of the direction opposition to the actual flow of the current. The induced EMF opposed the growth of the current and the growth of the magnetic field. The increase of the current that has not set up the magnetic field. There would be no opposition for the growth of the whole reaction. And opposition is called for the creation and collapse of the magnetic field. The lines of which they expand, contract, cut across the conductor and develop the counter EMF. Small circuits have conductors in them. You can assume that all the conductors and inductance That you can assume that all circuits have inductancy, and however the inductancy of the grid effect only when there is change in the current. The inductancy does not apply to the current, only changing the current when the current is constantly changing, and any of the AC circuit induces more than effect. Alright, define induction. What is meant by the EMF of the counter EMF? The Lenz Law. What is the effect that does the induced in the steady of the direct current and the direct current while it's changing amplitude? To increase the property of the induction of the conductor, it can be formed with a loop of the coil. Coil is also called an inductor. For the figure 2-3, the show of the conductor formed in the coil of the current in the one loop produced the magnetic field of the encircle the loop in the direction shown figure 2-3A, with the current increase of the magnetic field expand with the cut-all loops as shown figure 2-3B. The current in each loop affects all of the other loops. The field cutting other loop has effect increasing opposite to the current change. Figure 2-3 shows inductance. The coil shows the A and the B, and also B. Inductors are classified according to core type. The core center of the inductor just as for the core of an apple, center of the apple with the inductor cable. Inductor is made of the form of the coil wire around the core. The core material is normally one of the two basic types. Soft iron or air iron core inductor with a schematic with a symbol that will be represented with the lines across the top of the indicator of the presence of the iron core are shown in figure 3-4A. The air core inductor may be nothing more than a coil wire, but it's usually coil formed around the hollow form of some non-magnetic material such as cardboard. The material serves as no purpose other than hold the shape of the coil. An air coil inductor is the schematics shown and symbol is shown in figure 2-4B. Alright, inductor iron core shown there, and inductor air core shown in B. Factors affecting coil inductance. There are several physical factors that affect the inductance of the coil. They include the number of the turns of the coil, the diameter of the coil length, the type of the materials used within the core, the number of the layers winding in the coil. The inductancy depends entirely on the physical construction of the circuit that can only be measured with a special laboratory instrument. Other factors mentioned consider first out the number of the turns after the inductancy with the coil. Figure 2-4-5 shows the two coils of the circle. Coil A has two coils and the coil B has 4 turn coils. Coil A flux field set up by the one cut loops of the other loop, and coil B the flux field set up by the one loop of the coil, 3 loops and then 3 other loops. Double the number of turns of the coil to produce the field twice with the strong. If the same current is used with the field twice as strong, cutting the twice the number of the turns will induce the 4 times voltage. Therefore, it is said the inductance varies in square number of the turns. And the inductancy factors of the number turn A and B. The second factor of the coil diameter in figure 2-6, again, you can see that the coil of UB, the twice of the diameter of the coil of UA, physically the returns more requires more than constructing a coil larger diameter of the one of the small diameter to equal the number of the turns. Therefore, the more lines of force exists and induce the counter EMF. In the coil of the larger diameter, actually inductance of the coil increases directly as the crossing of the sectional area. With the crossing increase, the recall the formula with the area of the circle. Area is pi times R2 radius squared, doubling the radius of the coil, increase the inductance factor by 4. Figure 2-6 shows the inductance diameter, figure diameter A, and double the diameter, doubling the radius of a coil, increase the inductance by a factor of 4. Alright, the third factor effect for the inductancy of the coil length of the coil. Figure 2-7 show with the two examples of the coil spacing. Coil A has 3 turns rather than widely spaced, making a relatively long coil. With the coil has types of few flux linkages due to the great distance between each other. There are coil with a relatively low induced. Coil B has close space turns, making the relatively short coil. This coil space increases the flux linkage, increases inductancy of the coil, doubling the length of the coil while keeping the same number of the turns, half the value of the inductance. Okay, so half the length, doubling the length will keep it in the same number of the terms of value of the, so you double the length, Alright, inductance coil length of the closely wound. The fourth physical factor of the type of the core material used with the coil figure 2-8 show with the 2 coil with the air coil, with the coil B with the soft iron core, with the magnetic core coil with the better path of the 4 magnetics of the force, with the non-magnetic core with the coil with the soft iron magnetic core is high. Permeability has less reluctancy magnetic force, resulting in more magnetic lines of force. This increases the magnetic lines of force, increases the number of lines of force with cutting each of the loop over the coil. Increases the inductancy of the coil should now be apparent with the inductancy of the coil increases directly. Permeability of the coil material increases. A is the air core, B is the soft iron core. These two figure 2H are the inductance factor core material. Another way increasing the inductancy of the wind the coil in layer with the figure 2-9 with the 3 core with a different amount for the layer with the coil with the figure 2-9A with the poor inductive compared to the others and the figure shown with the torn in a widely spaced layer and no layering flux movement indicated by the dash arrow that does not link it in fact because of the only layer with one turn. More inductive coil shown in figure 2.9b, but the turns closely closely spaced with the wire wounded by the two layers. The two layers link each other with a greater number of the flux loops during the flux of movement is not nearly all turns such as X or X of the four other turns shaded. This cut of the flux linkage to be increased. Shows A, B, and then C. Coils of various inductancy. A would be a coil. B is a more inductive coil. And C is a coil can be made still more inductive with the bi-winding 3-layer with the shown figure 2.9c. The increased number of the layer with the cross-section improve with the flux is linked even more with the number of safe some terms such as Y likely direct and 6 other turn shape with the actual practice for the layering with the continuing many more layers. Important factor to remember, however, the inductance of the coil increases with each layer added. Have you seen several factors that can affect the inductancy for the coil? All the factors for the variable, the more differently constructed coil will have the same inductance for the important information to remember. However, the inductancy depends upon the degree of the linkage between the wire with the conductor electromagnetic field, the straight link with the conductor, the very little flux of the linkage between one part of the conductor to another. And therefore, inductancy is extremely small, and it was shown with the conductors much more inductive when they are wound into coils. The true because of the maximum flux linkage between the conductor turns, which lies side by side in the coil. Question 7. Live factors affect the inductancy of the coil. Bending a straight piece of wire into a loop of the coil have an effect of the inductancy of the wire current, doubling the number of the turns, and the effect of the inductancy of the coil, doubling the diameter of the coil have the inductancy of the coil. That would be 4 times the insert of the soft iron core that has the effect of the inductancy of the coil. Increasing the number of the layer of the windings of the coil will affect the inductancy of the coil. Unit of the inductancy. As stated before, the basic unit for inductancy is L and is in the Henry, named after Joseph Henry, the co-discoverer of Farad, with the principle of electromagnetic induction. An inductor has the inductancy of 1 Henry if the EMF of 1 volt is induced in the inductor, while the current of the inductor changing with the rate of the 1 ampere per second. The relationship is between the induced voltage inductancy with the rate of the change of the current in respect of the time and state of mechanically as voltage inductancy is equal to the inductancy over, I haven't met that symbol yet, but was the Greek letter for delta, where voltage inductancy is induced in the EMF, that would be the inductancy in Henrys. L would be the inductancy in Henrys, and the triangle or the delta I is the change of the current in amperes occurs in at t sec and in seconds. Meaning change in the Henry is larger unit inductance U with a relatively large inductor. Small inductors, a mil-Henry U. The mil-Henry is equal to 1 times 10 to the negative 3 Henry. 1 Henry is equal to 1,000 millihenries. For still smaller inductors, use of inductors, the micro-Henry U8, micro-Henry is equal to 1 times 10 to the negative 6 Henries. 1 Henry is equal to 1,000, 1 Henry is equal to 1 million micro-Henries. Alright, growth and decay of the current over the Henry Henry series circuit. When the battery is connected with the pure inductance with the current bill with the final value to determine the defined value when pure inductance for the current builds up the final value at the rate determined the battery voltage and internal resistance of the battery, the current is built up. So once again, L is the symbol for inductancy in Henrys. Square, the triangle or the delta symbol for I is the change of the current in amperes and T milliseconds. That's what that says. So voltage inductancy is equal to Henrys times the change in current in amperes over the occurring in seconds, which would be the gradual because of the counter EMF generated with itself the inductance via the coil. When the current starts to flow over the magnetic line with the force outward over the coil of the lines coil, cut the turns of the wire on the inductor, build up the counter EMF up over the EMF of the battery. The opposition cut the delay with the time of the current with the build up, then save out with the batteries disconnected the line with the force collapse. against the lines of the cuts and turns inductor build up, and the EMF tends to prolong the flow of the current. The voltage divider containing the resistance inductancy may be connected in the circuit means of the special switch is shown in Figure 210A. This such series arrangement is the Henry or series circuit, or the LR circuit. I'm not sure what that stands for, but you see the switch 2 is closed and into ship 1. The battery goes in direct current around the there's a conduction coil. It's an L for the Henrys, and R for the ohms. This shows the voltage, voltage Henrys, the voltage ohms. Your growth in switch 1 and switch 2 decay. When switch 1 is closed, the voltage of the voltage to the whole voltage appear with across the voltage divider. The instant of the current increment with increase the maximum voltage. However, the instantaneous current change of the coil of the Henrys to produce the back of the EMF. To produce back EMF, which opposes the polarity almost equal to the EMF of the source. The back EMF opposed to the rapid current change. The Figure 210B shows the instant switch of the switch 1 and close the no measurable growth in the amperage G or amperage minimum voltage drop in the across of the resistor. Minimum voltage drop across the resistor and maximum voltage across the inductor L. Or inductors Henrys. As current starts the flow of the voltage ER across the the voltage across the indicator reduced the same amount with the fact that the voltage across the inductor Henrys to reduce by Henrys is reduced by the means that the growth of the current or amperes growth is increased consequently with the voltage across the voltage voltage reduced. Figure 210B shows the voltage of the across the indicator with the voltage Henry finally put the zero for the growth of the amperage growth of the growth stop increasing while the voltage across the resistor of the voltage voltage reduced below the value of the equal to the source of the value voltage electrical voltage toll. And electrical induced to the mechanical and aerial growth of the current of the electric circuit will be like the acceleration of the boat with the surface of water. The boat does not move in the instant of the constant of the force is applied. The instant of the applied force that is used to overcome the inertia of the boat. But once the inertia is overcome, the boat will start to move. After a while, the speed of the boat reaches the maximum value applied force is used to overcoming the friction of the water against the hull. When the battery of the switch is switch 1 is in the Henry ohms of circuit, the Figure 210A will close with the rate over the current with the increase of the maximum inductive coil. The instrument of the battery voltage used to overcome the EMF of the self-inducing maximum because of the rate of the change of the current is maximum. Thus, the battery voltage is equal to the drop of the current of the inductor, but the voltage drop of the resistor is 0. So the battery is equal to the drop of the inductor and the voltage curve of the resistor is 0. As the time goes on, the battery voltage appears with the curve of the resistor with the loss less across the inductor. The rate of change of the current is less than inducer, and the EMF is less than steady state condition, but the current is approached. The drop across the inductor approaches 0 with all the battery's voltage dropped across the resistance of the circuit. The voltage across the inductor resistor change with the magnitude during the period of the growth of the circuit of the current same way of the force applied with the boat divided in itself between the effects of the inherent and friction. In both examples, the forces developed in first across the inherent inductive effectively, finally across the friction resistive effect. Figure 210C shows that the switch 2 is glove with the source of voltage of the total voltage removed from the circuit of the flux that has been established with around the inductor L or inductor L. Collapse the windows and a voltage of the inductor and inductor of the polarity of the voltage opposite voltage toll. The essential of the voltage toll is magnitude of the induced voltage covered or decaying current or ID. Or amperage decayed, and the flow of the resistor ohms the same direction with the current with the flowing with the original switch 1 was flow of the voltage reduced. It is initial equals the source of the voltage total is developing across the resistance or the ohms. The voltage across the resistor is the voltage resistor. Voltage resistance rapidly fall to 0 with the voltage across the inductor or the voltage induced falls to 0 due to the collapse of collapsing flux. Just an example of the voltage used to explain with the growth of the current in circuit. It can also be used to explain with the decay of the current in circuit with the force of the growth applied with the boat with the remove of the boat, still continue to move the through the water while the eventually coming to the top of the peak of the energy will be stored within the air with the movement of the boat. The period of time when the friction over the water occurs overcome to the air of the boat. The boat stops and moves with the adjustments. The errant boat stored energy of the magnetic field of the inductor stores energy because of the even in the power it stores and removed. Source is removed. The stored energy of the magnetic field of the inductor tends to keep the current from flowing in the circuit until the magnetic field is collapsed. Our question A: what is the voltage applied when the series of the inductor resistance circuit? However, the opposition of does not in the inductance flow of the current compared with the circuit of the resistance series of the circuit of the resistance of the resistor 1 and the inductor 1. Of the voltage exists across resistor 1 with the current AMF at the maximum value. Or what happens to the voltage? What happens to the voltage across the resistance of the inductor resistor circuit and resistance circuit during the current buildup in the circuit during the current decay in the circuit? All right, LR inductancy over resistancy time constant available to determine the time required for the current inductor to reach a specific value shown in Figure 211. The inductancy over the resistancy time constant is the time required for the current inductor to increase to 63% or 63.2% of the maximum current. The time constant is equal to the time required for the current increase by 63.2% of the difference of the value between the current flow of the inductor maximum current. The maximum current flows in the inductor are 5 inductances over the 5 inductance over ohms resistance completed constant completed. The following examples show the clear of the confusing time constant. Assume that the maximum current is the inductancy of the resistance circuit and the 10 amperes is known by the circuit energizer that takes the current to go from 0 to 10 amperes. The first time constant is completed with the current circuit at 63.2% of 10 amperes. The amplitude of the current and the end of one time constant is 63.2 amps. This shows your amperes inductancy over the fraction 1 to the growth constant of the inductancy over the ohms or inductancy over resistancy. Show the growth and then the decay. During the second time of the constant of the current engine again increased to 63.2, the difference of the value become the current flow of the inductor maximum from the difference of the 10 amperes by 63.2 amperes equals to 3.68 equal 3.682 amperes. 63.2 of the 3.68 amperes is 2.32 amperes. This is increased during the second time of the constant and added to the first time of the constant. Thus, upon the completion of the second time constant, the amount of the inductancy resistance circuit is 63.2 plus 2.32 amperes of 8.643 amperes. During the third constant current arrangement, these are the time constants. Notice they're going 1, 2. This one was 63.2. This one's 86.5 or 86.4. And then your third one would be 9.5. During the third constant, the A again increases the 10 amperes of the 8.64 equals 1.36, 1.36 plus 63.2% is 0.86 amperes, or 8.64 amperes plus 0.86 is 9.5 amperes. Then the fourth constant, you would have 9.8, or 10 amperes times minus 9.5 amperes, and your third constant gives you half an ampere plus the 63.2% is 3.16 amperes. And then you take your third constant, add that ampere, and you get 9.82 amperes. And this is the, remember, this is the growth. The fifth time constant is current increase of the 10 amperes, the 9.82 amperes you get, minus the fifth constant times minus the fourth constant, the fourth constant times the, that difference, the, your amperage difference times 6.32% equals 1.14 or 9.82 amperes plus 1.4, your fourth constant plus the fifth constant equals your 9.93 amperes. So if the current end of the fifth time of the constant is almost equal to 10 amperes, the maximum current for all purposes of the slightly difference value can be ignored. When the inductancy resistance circuit is de-energized, the circuit current decays to zero in 5 times the constant, same rate with the previously increased. Alright, so it will drop in 5 times the constant. So that's like a radius, I believe. When the load resistance circuit is de-energized, the circuit decreases 0 to 5 times the constant at the same rate with the previously increased. For the growth decay of the current is the load resistor circuit. Are plotted in the graph. The curve appears in Figure 211. Note that the current increases and decays at the same rate of 5 time constant. The value of the time constant is the seconds is equal to the henries divided by the circuit with the resistance. So the formula to calculate the inductancy of the over resistance time is the time and constants is the number of henries over the ohms. When the formula is the henries over ohms and time constant, the maximum current applied with the inductor is 1.8 amperes. The current flowed in the inductor 3 times the constant after the circuit was first de-energized. The maximum number of the time constant required by the current of the amperes, the henries, the inductancy resistant current of the increase of the maximum value. Circuit current turning the inductor's resistor is a maximum of 12 amperes applied with the current flowing after the fifth constant of the time constant, the fifth time constant of the inductancy and resistors. The circuit is open within how many times the constant is required for the current decay of 1.625 amperes. Alright, power loss in an inductor. Since the inductor coil consists of the number of the terms of wires, since all wires have some of the resistance, every inductor current has a certain amount of resistance. Normally the resistance is small, usually neglected solving the various type of the AC circuit problems because of the resistance of the inductor of opposition and alternating current, which will be discussed later, is much greater than the resistance of the negligible effect on the current. However, some of the inductors are designed to carry relatively large amount of the current. Considerable power will dissipate with the inductor, even though the amount of resistor is indicated within the indicator inductor resistance in the inductor is small. The power that is wasted power is called the copper loss. Copper loss of the inductor can be calculated multiplying the square of the current inductor resistance of the winding of amperes squared over ohms. The addition of the copper loss iron core with the inductor has 2 iron losses. They are called the hysteresis loss and the eddy current loss. The hysteresis loss is due to the power that is consumed reversing the magnetic field of the inductor core at each time the direction of the current inductor changes. The eddy current is due to the heat of the core, calculating the current induced of the iron core with the magnetic field around. The eddy current is due to the heating of the core circulation of the current inducing of the iron core magnetic field around the turns of the coil. Once again, hysteresis loss is due to the power consumed by the reversing of the magnetic field of the inductor core each time the direction of the current is inductor change. Eddy current is lawfully due to the heating of the core of the circulating currents that induce the iron core of the magnetic field around the turns of the coil. These currents are called eddy currents and circulate within the iron core only. All the loss is dissipated with the power in form of heat. Since the power cannot be returned to the electrical circuit, it's lost power. Question 11. State the types of power lost in the inductor. Mutual inductance. When two coils are located with the flux of one coil links with the turn of the other, the coil will change the flux in one coil cause the EMF then due for the other coil. They allow for the energy from one coil to be transferred coupled to the other. The two coils are said to be coupled and linked by the property of mutual inductance, or M. The amount of the mutual inductance depends on the relative position of the two coils. As shown in Figure 212, the coils separated considerable distance. The amount of the flux uncommon with the both coils and small mutual index low. Conversely, if the coils are close together so that nearly all flux one coil links to turn to the other, mutual inductance high. The mutual inductance can increase greatly by the amount of the coil on the common iron core. A shows the inductor of the closed and large M, or mutual inductancy. Length of the coil 1, length of the coil 2. Notice that the 2 has more wraps than 1. L inductors far apart. Smaller M, or mutual inductancy. C. Indicator inductor axis perpendicular. No. M. So the effect for the position of mutual inductance. Two coils are placed close together, shown figure 213. Coil 1 is connected to the battery through switch S, and coil 2 is connected to an ammeter, which the S is coiled with the figure 213A. The current flow for the coil 1 sets up the magnetic field, and the length of the coil 2 causes the inducing voltage for the coil 2. Monetary deflection of the ammeter of the current of the coil reach of the state value of the ammeter returns to 0. The switch S is now open. The figure 213B with the ammeter deflect with the monetary opposite direction, indicating monetary flow of the current opposite direction of the coil 2 when the current coil 2 is produced with the collapsing magnetic field of the coil 1. So it shows mutual inductance, coil 1, expanding flux, switch is closed. The switch on coil 1 is closed. Switch is open, show the collapsing flux, coil 1, coil 2. Notice that they... Alright, define mutual inductancy. Factors affecting mutual inductancy. Mutual inductancy of two adjacent coils is dependent on the physical dimension of the two coils, the number of the turns each coil, the distance between the two coils, relative position and the axis of the two coils, permeability of the cores, coefficiency of coupling between two coils equal the ratio of the flux cutting of one of the coil flux originating of the other coil. The two coils are positioned with respect to each other so that they are all flux of the one coil cut. The turns of the coils are said to have the unity efficiency of coupling never equal to any unity, but it approaches the value with a certain type of the coupling device with flux produced in one coil cuts only half the turns of the other coil. The coefficient of the coupling is 0.5. The coefficient of the coupling is designated letter K. The mutual the coupling of the coefficient coupling is designated letter K. All right, then mutual inductancy two coils. Inductancy coil 1, inductancy coil 2 is expressed in terms of the inductancy each for the coil coefficient of the coupling K is a formula, whereas the mutual inductancy is equal to the coefficient of the coupling over the square root of the inductancy coil 1 times the inductancy coil 2 in henries. Example: 10 henries. The coil 1, 2, and 10 Henry coil and one 200 20 Henry coil are connected with a series. The physical closing enough. The other coefficient of the coupling is 0.5, and physical close enough to have the other, so that the coupling is 0.5. With a mutual inductancy between the coils, you have the mutual inductancy of K equals the square root of the coil 1 comes inductancy coil 1 over inductancy coil 2. You times inductancy the henries. You get 200 henries times the coefficient of the coupling, 0.5, which gives you, and the square root of 200 would be 14.4 H, or mutual inductancy 707 henries. What are the two circuits said to be coupled when met with the coefficient of the coupling? Series inductors without magnetic coupling with the inductor will shield located at far enough apart with one another. The effect with the mutual inductancy is there is no mutual inductancy magnetic coupling with inductor with a connected in series. The total inductancy is equal to the sum of so when the series inductors without magnetic couplings, inductors well shielded are located far enough to one part when the effect with the mutual inductancy negligible, no mutual inductancy magnetic coil. The inductors are connected in series. Total inductance is equal to the sum of the individual inductances as the formula. Total inductancy is equal to inductancy coil 1, 2, and 3, or however the number. Now, all the number, adding all the inductancy coils together. When inductancy totals induction coil 1, 2, and 3, the induction 1, 2, and 3 is and induction number means that any number of the inductors may be U. The inductor of the inductors in series are added together like a resistance in series. Or a series inductor with a magnetic coupling. The two inductors series are arranged with the field with one links to the other and combined with the inductancy to determine the flow. The inductancy total of the inductancy 1, 2, and 3 is equal to plus or minus the mutual inductance between the two inductors. The total inductancy is equal to the inductancy of the inductances 1 and 2, and M, the mutual inductance between two conductors. So we take the mutual inductancy of the equal the coefficient of the coupling over the square root of the inductancy of the coil. So you take and then the plus sign of the Mutual inductancy of magnetic field with the two indicators aiding each other. They're shown in Figure 214. Mutual sign of the mutual inductancy when the magnetic field of the two inductors oppose each other. They're shown in Figure 215. The factor 2 M accounts for the influence of the resistor 2 1 on 2 and resistor 2 on 1. Great, noted. All right. So you have a series inductor with adding fields. Series inductor with opposing fields. Example: the 10 Henry coil is in series with the 5 coil. If 10 coil Henry is in series with the 5 coil, so fields aid each other. The mutual inductancy is 7 Henrys. What is the combined inductancy of the coils? You have your inductancy total is 10 and 5 Henrys. So 2 times 7 Henrys would be your inductancy. Mutual inductancy, you have 29 Henrys. Alright, 2 series connected with the 7 Henrys. Inductors are adjacent to each other. The coefficient of coupling with a 0.64 with the value of the mutual inductance circuit. A circuit contains 2 series of inductors aligned within such a way that the magnetic fields opposing each other. The formula should be U to compute the total inductancy in the circuit. The magnetic field of the 2 coils are adding to each other. The inductancy coil with 3 Henrys and 5 Henrys, respectively. The coil mutual inductance. The coil's mutual inductancy is 5. Was a combined inductancy. Also, pair-wall inductors without coupling. The total inductancy of the inductors is pair-wall is calculated with the same number of the total resistors and the pair-wall calculated provided the coefficient of the coupling between the coils is 0, and expressed mathematically is the reciprocal of the load total. The total load equals the series added together and would equal the 1 over the inductor's number, the number of the inductor's inductancy. All right, summary, chapter 2.